All right, so this is chapter 9. And in this chapter, we are going to learn about a very important concept known as momentum. So, for momentum, we will be looking at collisions. And generally, the best way to describe collision is, using this concept of momentum and impulse, which we'll be covering in this chapter. All right, so the chapter goal is to understand and apply the new concept of impulse and momentum. All right, so one of the things that we're going to be, as I mentioned, right, considering in this chapter are collisions, and the collisions basically are using the previous concept that we learned, like force, mass, velocity, and things like that. In a way, we're just basically using all of those all those old concepts, but the idea here is this. For example, let's say here's a wall and you have two objects and still could be represented as a particle. Let's say two objects moving toward this wall. Let's say this is mass 1, object 1 with velocity 1, mass 2, and this is velocity 2. And let's say they both have even the same velocity. So let's say this is 10 meter per second, which is roughly 20 miles an hour. So let's say 10 meters per second, both objects moving toward the wall with a 10 meter per second velocity. Now the question here is this: which object will cause more damage? Object 1 or object 2? Well, both of them moving with the same speed. So probably you will think, oh, they're probably going to do the same damage. But not quite, right? Because we're not given enough information. We don't know what are objects 1 and 2 and what are the differences between them. For example, what if object 1 is just a mosquito moving at 10 meter per second and colliding with the wall? Barely any damage, right? How about object 2? It's an elephant moving at 10 meter per second and colliding with a wall or a car, right? So you can see what a big difference, right? So let's say this is 0.001 kilogram compared to something there's maybe 1,000 kilogram. Damage will be completely different, right? Depending on if we include also the mass as part of the let's say problem. And that's what we're going to be doing in this chapter. Because when you talk about collisions, not only velocity, but then the mass of the object also come into play. So that's why when you take the mass and velocity combined together, so the product of mass and velocity is what we defined to be object's momentum. So you can see, right, the momentum of the object is defined as mass times velocity. And you can see right over here, the elephant will have a momentum that is almost a million times bigger, right? Because one is 0.0001, which is this is like, let's say, 10 to the negative 3. This one is 10 to the 3. The difference is almost 10 to the 6. So you get much bigger difference in momentum. And that's what we have. So momentum is defined as mass of the object in kilograms times the velocity of the object in meter per second. So the units are kilograms times meter per second. And it's also a vector, right? It's also a vector where since mass is a scalar, velocity is a vector, then momentum pretty much always has the same velocity, same direction as velocity. So think like this. Then if you have an object who is at rest, then its momentum, which is m times v, will be zero, since it has a mass but it has no velocity. We will never really consider object with no mass. Technically there is such thing, right? So we have let's say a photon, which is the particle of light, has technically no mass, but those are the things that we will learn in physics 222, and if you get lucky that let's say to get to those chapters. But in any case, the idea here is we're going to usually assume that mass is constant. If you're given some kind of mass, the object's mass basically is constant, and momentum is basically can be zero due to only velocity being zero. All right, so you can see, right, if you have an object with mass m moving with this velocity, which is a two-dimensional velocity, then momentum is m times v, and momentum is in the same direction as velocity. If velocity happened to be two-dimensional, then the momentum is two-dimensional. It has x and y components according to the x and y component of the velocity too, right? Because velocity two-dimensional means it has components. That means, momentum has components. All right, in any case, one of the most important thing then is when object changes momentum. Okay, so what happens, when object goes from point A to point B and then velocity changes and things like that. So by looking at the change in momentum, we can, figure out number of things. And remember, in a way, what we're saying here is there's a delta P changing momentum, which is P final minus P initial. Object's momentum after minus object's momentum before, and we are in a way dealing with vectors, so you have to be careful with the direction, negative, positive, right, depending in which direction object is moving. So let's look at an example here. So let's say we have a cart moving to the left with 2 meters per second, and it's a 10-kilogram cart, and then it collides with the wall and then bounces back and moves basically to the right with 1 meter per second. So then what is the cart's change of momentum? Delta px. X subscript means that it's only horizontal, motion in a way. So one thing we can do here, we can say, all right, so then delta px is equals to, well, p final minus p initial, which is then, since momentum is defined as mass times velocity, so it will be mass times final velocity minus mass times initial velocity. We can factor out mass and say then this is just v final minus v initial. Now equals mass times, let me already plug in the values. So let's say 10 kilograms times final velocity is 1 meter per second minus initial velocity, then 2 meter per second, but to the left, so it's negative 2 meter per second. That means this is 10 kilograms times 1 plus 2, so basically 3 meters per second. And what we get 30 kilograms meter per second. And that's my change in horizontal momentum of the object. And that's what we have. When you look at the momentum, right, more important is change in momentum rather than just momentum at one point or another. Momentum at one point or another will tell you this. Does your object have, velocity, right? If you have a momentum, you have a velocity. If you don't have a momentum, it means you're at rest. So momentum at one point will tell you basically if you have a velocity and also in which direction you have a velocity. But then you're not really going to be able to tell what happens to your object unless you look at the change in momentum. And that's here what we have. Changing momentum is positive, right? So that means, in a way, basically the object, changes direction. That's kind of one of the things you can think of like that. All right, so as I mentioned, the momentum is very important and very useful when we consider collisions. And you can see, right, collisions is like a tennis ball striking the racket, is a very, uh, let's say, interaction between two objects, right, a racket and a tennis ball, and that happens very quickly. But even if it happens very quickly, there's a finite time that we have to take into account. So that's why we can say that it's a short duration interaction, but I mean such that delta t technically can be measured, can be calculated, and things like that. So not none of the collisions are instantaneous, right? It doesn't take like a trillionth of a second. No, it's usually like a millisecond or a microsecond maybe, but most of the time it's probably going to be millisecond or maybe like let's say a second or so. Right. So also one of the things you will see here is that the object that we're dealing with, whatever the object is, like a tennis ball or a car striking a wall or I don't know, anything, right? So basically every object has a little bit of elasticity. So look at the tennis ball. See, this is during the collision. You can see that the shape of the ball. So it's kind of round over here, but not so over here. What happens is, well, it's being compressed. So that means there is um, the reason that there's a like little bit of delta t, right, for the collision, because the object technically is compressed and then re-expanded, during the collision. Okay, so that's kind of one of the things we're going to be seeing, and we can even plot that. So for example, think like this. Let's say this is a tennis ball, so it's moving to the left, and then let's say there's a racket, right? There's a racket which exerts force, and then makes the tennis ball move in opposite direction. Okay, so this force that acting on the object during the collision is known as an impulsive force. Okay, it's impulsive force. And impulsive force is basically the one that, changes the momentum of the object. We will see in a little bit. But we can also look at it in terms of, this force, right, acting on the object, doing some, as a function of time. So like, let's say, if we plot this, this is the impulsive force on the y-axis, and the time on the let's say x-axis, we can see, right. So this is the region where the ball was moving to the left, and then here is where the ball makes contact with the racket, and then there's compression. That means as the ball is compressing, the force starts increasing until it reaches some maximum value. And then once you get that maximum value, you can say that you achieved maximum compression. After that, it starts re-expanding, and then this is an expansion where the force decreases until it gets to zero, and this is where the contact ends. And this is the region, right, that represents basically uh, the force acting on the object during that, delta t, right, that time interval, so duration of the collision. So as I said, right, we're not talking about time in terms of how long does it take for this guy to reach here or move to the other direction. We only care about delta t for the collision. That means that's the time during the collision of the object with some kind of wall or a ground or whatever it is, right, a rocket or thing like that. And obviously, the momentum here is changed. And even if you had the same speed, like let's say this is 10 meter per second negative I hat, this is 10 meter per second I hat, well, there is still change in velocity and change in momentum. Why? Because there's a direction change. So momentum is different before and after. So that's one of the things that you're going to need to, understand. All right. So let's then see in terms of why the momentum concept is kind of fundamental. Well, because this is how we define Newton's second law, but this is not actually how the second law was defined by, the person who wrote that, which is Isaac Newton. He didn't write it in terms of acceleration. Remember, acceleration is the derivative of velocity with respect to time. So m times a becomes m dv dt. M is a scalar. We can actually move that inside. So it becomes, dmv dt. Well, we just learned, right, m times v is nothing but the momentum. That means force is actually not mass times acceleration, but force is the rate at which object changes its momentum. That means, for example, think like this. You have an object sitting there with mass m and with no initial velocity. That means what is the initial momentum? Well, it's zero, right, as we talked about. Now, how do we change the momentum of this object? How can we change it? Well, obviously we can apply force. And if you apply force, it starts moving. And what happens when it starts moving? It has a momentum now. So it goes from zero momentum to some kind of non-zero momentum, right? And means that we change the momentum. And the force basically is equal to the rate at which we change the momentum, dp dt. So that's the important thing. That means, that's why it is fundamental, because, uh, you know, before, right, we kind of decided to use acceleration. Before it was like, let's say, in terms of momentum. So we were looking at not, objects speeding up or slowing down as, in terms of, oh, there's acceleration. We would say that if you're speeding up, then you're increasing your momentum. If you're slowing down, you're decreasing your momentum. So it was everything basically in terms of momentum. And what changes momentum? Well, external force. That's kind of what we have. So also, if we take this equation, right, F, equals dp dt. So again, so this is, remember, this is down external force technically. It equals to dp dt. If I rearrange it in a way that I move the dt to the other side, so basically I have, d thing like this. So I'm writing as like this, which is, let me do it here so you guys can see. So thing like this. So dp equals then external force dt, basically rearranging this like that, and then integrating both sides. So this one will be from P initial to P final. And the left side integral is very simple because you're integrating in terms of dp, becomes, P from the, with limits P final, P initial, which then becomes, P final minus P initial. Okay. That means the left side becomes P final minus P initial, which is nothing but delta P. The right side, we have this. integral of f dt. Okay, so then let's see what we get with that. So you can see in terms of here, what I have is the left side becomes dp, delta p, which is p final x minus p initial x. The right side becomes f of x dt, f of x of t, right, dt. And the limits are t initial, t final. So this what we have for the, you know, impulsive force acting on the object to change its momentum during this dt, time interval. Right. So what we do here is we, take the right side of the equation, this guy with this integral, and we call this impulse. The f of x is impulsive force, but this integral is called impulse. That means impulse, which is, given with a j, so j of x, right, the x component, is then defined as the integral of f of x dt, and in the graph that I just showed you earlier, right, f of, t, so something like that, it equals to the area under the graph, right? So that means in impulse, which is, in a way, you can think like, let's say it's the impulsive force times the, time interval of the collision, and you get that. All right, so think like this: if the force is constant, you can remove this, of the integral, and then you have then basically t initial, t final dt, and this just becomes f of x delta t. Simple as that. If your force is not constant, then you get to integrate. But if the force is constant, it becomes as simple as that. Okay. So and it has a unit of newtons per second, because it's newtons times seconds. All right. So but see, this is, which is now I can say is impulse, right, is also equals to the change in momentum. But change in momentum had an equation kilograms meter per second, and this one is newtons times seconds. Well, which means they're also equivalent. Newtons times seconds is equivalent to kilograms times meter per second, which you should be able to derive, no problem with that. All right, so again, so if I come back to this graph, as I mentioned, right, so then the area under this graph is what we can then define to be the impulse. All right, so the impulse is a vector, right, is a vector. So this is a positive impulse, then something like this will be a negative impulse, right, because the force is negative and things like that. And it always has the same direction as the force itself. Okay. Now, obviously, when you have a graph like this, it's difficult to find the value of the impulse doing the, using the graph. But if you have the maximum force, you can more or less, kind of, rearrange this graph into something like average force rather than maximum force. Rather than this goes from 0 to some f max, and then from f max to 0, you can say that during the entire time there was some kind of average force. How can we find average force? Well, it's always going to be equal to the f max, half of f max. That means average force is equal to the half of the maximum force. So then I can say then, all right, so instead of using, f as a function of time, I can find half of the maximum force to be f average, and I can say during this entire time force was constant and it was equal to the average, force. That's why, I can get something like that. Because if f average is constant during the entire time, then it just becomes simply f average times delta t. Now, remember, the left side of that equation, Newton's second law, was the, kind of like, let's say, change in momentum. The right side was the integral, which then we define to be the impulse. Well, then we can say that impulse is equals to the change in momentum. So this is known as the impulse momentum theorem. So the particle experiences an impulsive force in the x direction, and the impulsive force delivered to the particle is equals to the change in the particle momentum. Okay, so sometimes you can rewrite this as delta p, which is p final minus p initial, equals jx, and then you can say p final equals p initial plus jx, right? Moving the p initial to the other side, which means like this. So if there is no impulse, object's momentum before and after is the same. But if there is an impulse, then momentum changes depending what you have, right? If you have a positive, if you have impulse in the same direction as the momentum, original momentum, then object increases its momentum in that direction. If it's basically equals to the, momentum before, but in the opposite direction, you can cancel it, and so on and so forth. That means this is kind of like a little more easier to visualize what happens to the final momentum depending on, basically depending on this guy over here. So, for example, a rubber ball bounces off a wall. So that's basically an object moving to the right with the positive velocity, hits the wall. Well, wall exerts a force, impulsive force, right? It's basically a normal force. But then if I'm graphing this, it's going to be, all right, so here's a force acting as a function of time. So it's going to be like this, and it's going to be negative graph. Why negative? Well, the force is to the left, right? Force is to the left. So then what I can do here is I can say then, all right, so if I have the delta t, so if I'm doing the momentum graph, I can say, all right, so the momentum is positive because object is moving to the left, to the right. And then there's a change in momentum because after the collision, it's moving to the left. That means the momentum will be negative. So that means there's this transition, right, from positive momentum to negative momentum. Okay. And I can always say that change in momentum, then it goes to the Jx, and Jx basically represented by that pretty much, that graph. That's basically, our Jx, because that's, what change in momentum represents. That was our change in momentum. All right, so you can write the impulse or area under the force curve has a negative value. So that's why this is a impulse, which is going to be a negative value. And this also represents basically delta P, which is also you consider a negative slope, which corresponds with, our impulse, right? All right, let's look at some, a few simple examples. You have a 2 kilogram object moving to the right with a speed of 0.5 meter per second, experiences force shown in the diagram. What are the object's speed and direction after the force ends? All right, so let's see what we have. So we're given mass, we're given the speed initial, right? And we're given the force versus time graph. And we're told that the delta t is half a second, and the force is constant for that half a second, and the magnitude is 2 newtons. So all right, that means I can do this. Delta p is equals to p final minus p initial, and this is equals to jx, which is equals to the average force times delta t. Then I can say p final equals to p initial plus f average delta t, which is basically my impulse. All right, so then what is P final? It's mass times V final. P initial, mass times V initial. Then plus average force, right, times delta T. Remember, my goal here is to find um, the final speed. And I can do that by first, let's say, finding the um, final momentum, which then will be 2 kilograms times 0.5 meter per second, then plus 2 newtons times half a second. So what I get here is 2 times 1/2, so it's 1 kilogram meter per second plus 2 times 1/2, then another 1 kilograms meter per second. So this is then 2 kilograms meter per second. That's my final moment. And since this is m times v final equals to that, then I can divide both sides by mass, which is 2 kilograms, right? Get rid of that, and then get plus 1 kilogram meters per second. And that's my final momentum. That's my final momentum, which basically, final speed is, sorry, guys. Kilograms cancel out. It's plus 1 meter per second. Now, the question is, did our momentum increase? Well, of course it did, because we were moving at half a meter per second. Now we're moving at 1 meter per second. That means the force delivered in the same direction as object motion increased its momentum. Here's another example. Basically, same conditions, but this time the force given with this diagram. All right, so let's see what we have. That means, again, we can say mv final equals mv initial plus f, delta t. So we can then again calculate this, right? So it's 2 times, 1/2 meter per second, then plus Now the average force is then negative 2 newtons times 1/2 second. Then what I'm going to get here is 1 kilogram meter per second from here, then minus 1 kilogram meter per second from there, and that equals to 0, which means my m times v final, the final momentum, equals to 0. What does it suggest? Well, it suggests that v final then equals to 0. That means the object comes to rest. That means whatever the force was exerted on the object basically made it stop in 1/2 second. All right, so here's another example. We have a time varying force this time. F of t equals at to the 4 plus bt squared acts for 0.5 seconds on a 12.25 kilogram object. Starting at time t equals 1 second. In the SI units, in the SI system, A has a numerical value of 4.5, B has a numerical value of 8.75. What are the SI units for A and B? Well, to understand this, we have to say, all right, so here's a force, and this is A to the T to the 4. That means this A times T to the 4, which is basically seconds to the 4, then plus B times T squared, which is seconds squared. And remember, the entire thing then has to be in newtons, right? Because, the left side is newtons, the right side, everything has to be newtons. That means A has to be then newtons per second to the 4 to cancel those, and B has to be newtons to the second square to cancel that. That means A has a units of newton to the second to the 4, and B has a units of newton per second square in order for this whole thing to work out. That should be simple enough. Part B says, then what impulse does this force impact to the object? Well, we know that Jx is equals to, or just J, right? So equals the integral of f of function of t dt. Then this is, let's say, t initial to t final. All right, so then we started with t equals 1 second, and we go to the, it says acts for 0.5 seconds. That means go from 1.5 seconds, from 1 second to 1.5 seconds. And then I have at to the 4 plus bt squared dt. All right. So then from here, what I do is basically, a times t5 over 5, then plus b times t cube over 3, and the limits are 1 to 1.5, basically, in terms of seconds. All right. So then we just pretty much do the, the tedious calculations and things like that. And, I'm sure you should be able to do that or follow the solution that I have. But, it's just simple enough that you guys can see that you're going to get 12.9 newtons. Okay. Newtons times seconds, sorry, 12.9 newtons times, that's for the Jx. 12.9 newtons times seconds. Those should be the units for the impulse. All right. That means if you have a time varying force, you need to pretty much plug in and integrate all that. All right, so sometimes you can also use a chart like this, which is, impulse, let's say momentum chart, which says that, let's say this is your initial momentum, and then this is the impulse. And if you add them together, right, you get your final momentum, which is basically both of them together. So this is momentum bar chart. Okay. So you can see, right, if you have a positive impulse and added to the positive initial momentum, your final momentum is positive and greater because you're just adding those two together. But you can also have, let's say, if the rubber ball was initially moving to the right, and then there's a negative impulse acting on it, so positive momentum but negative impulse. Well, this figure shows that the momentum bar chart is, again, it's a sum of them, but this is positive, this is negative. So this represents, in a way, their difference, right? This represents their difference, which basically gives you your final momentum. Now, what does it mean that if your final momentum is negative? Well, it just means that your object that was moving to the right now is moving to the left. Okay, it has a velocity to the left. And, I guess the bar chart tells you that they have about same momentum before and after, at least the magnitude. So that means it's moving with the same speed, but in opposite direction. All right. So let's look at then this example over here. All right. For a top player, tennis ball may leave the racket on the serve with a speed of 55 meters per second, which is about 120 miles an hour. If the ball has a mass of 0.06 kilogram and is in contact with the racket for about 4 milliseconds, estimate the average force on the ball. Would this force be large enough to lift a 60 kilogram person? All right, so let's do that. So first, we calculate that. So we're told that the speed here is 55 meters per second, right? So, and the ball has a mass of 0.6 kilogram. So we're given the speed, we're given the mass, and also we're given the time interval. We want to find the force. And we assume that this is um, average force because obviously, as we learned, right, a racket exerts variable force. So that, it's a, compression and expansion. So the force is not constant, but it's asking for the average. So we're fine with that. In any case, its change in momentum is equals to um, impulse, which is an F average times delta T. Now, remember, we assume that we are talking about the ball that, I don't know if you ever played the tennis or have seen the tennis, right? That the serve, basically you throw the ball in a vertical direction. So basically moving in a vertical direction, and then you strike it with the racket. And then we are looking at, when the force is like this, right? More or less. So then in a way, initially the object has no horizontal velocity because it's only moving vertically, and then you strike it in a horizontal direction. So the delta P, which is P final minus P initial, this is basically just P final minus zero because there's no momentum before. And this is equal to then F average delta T. Then F average, you can see, right, is nothing but P final over delta T. And this is where we do then mass times, final velocity over delta T. So we have 0.06 kilogram times 55 meter per second speed, and this is divided by 4 times 10 to the negative 3 seconds. We'll do this calculation. We should get 825 newtons. That's the amount of force. All right. So now, would this be large enough to lift a 60 kilogram person? Well, I don't know. Let's see. So the gravitational force, right, the weight of the 60 kilogram person is 60 kilograms times 9.8 meter per second square. Well, it's roughly, right, you can see, right, roughly 600 Newton. So this is more than enough. Imagine, right, then when someone like Roger Federer strikes the ball, right, during a serve, they exert over 800 Newton force, which is strong enough to lift a 60 kilogram, which is, kind of like, let's say, average, I guess average weight for, right, 60 kilogram, right? Or the average mass, right, for an adult. Um, and it's strong enough to lift it. Maybe even like 70, right? You can see even 80 kilogram object can be lifted because 80 kilogram object will give you roughly 800 newtons, and that's even that less than that. All right, so now one of the things we're going to do here is this. We're going to be learning one of our first conservation laws in this class. There are several ones that we're going to be looking at. So this one is known as a conservation of linear momentum. So later on, we can also learn about conservation of angular momentum, which is a little bit different. So, but this one is a conservation of linear momentum. That means we're talking about objects moving in a linear direction. So think like this. So you have two objects moving toward each other. You have object one with initial velocity to the right, object two with initial velocity to the left. They're moving toward each other. So this is known as before collision. And if I'm looking at the momentum of the system, which I'm going to take the system to be both of them together, momentum of the system before will be then initial momentum of one plus initial momentum of two. So this will be then M1 V1 initial plus M2 V2 initial. This is my momentum of the system before collision. Then they collide, clearly because they're moving toward each other. During the collision, the forces acting onto this net force is force that one exerts on two plus force that two exerts on one, because they exert force on one another. That's a during collision. Then obviously after the collision, they move sort of like in opposite directions. So then this will be the final momentum of the system, which will be P1 final plus P2 final, which I can write as M1 V1 final plus M2 V2 final. Okay. You can, if you want, you can put the X as a subscript as well, indicating that that's a horizontal, but, let's say to keep the subscript to a little bit minimal, right? Think of like right now, this was a horizontal, so we are considering just the horizontal, momentums. Now, here's one thing we have. Remember, we talked about, right, that momentum changes when there's an external force. That means what I have here is this. Delta P is equals to impulse, which is, integral of net force, technically dt. But here's the thing. If I'm close, if I have an isolated system, and my isolated system consists of those two balls and nothing else, and the forces in my system, only those two forces during the collision, well, those are action-reaction forces, where F12 is equals to the negative of F21. And this net force is going to give me 0, which means the right side of my equation is 0, because those are what we'll call internal forces. So internal forces and internal forces cancel each other. Now, what does it mean then in terms of delta P? Well, if the delta P equals 0, means P initial and P final are the same, which means the momentum of the system before collision and after collision is the same. I can completely then ignore what happens during the collision and just concentrate before and after. So this one is after collision, momentum of the system equals before collision, momentum of the system. Not the momentum of one or two, but both of them combined, some of them, all the system, the objects in my system. I can have maybe like 3 or 4 and things like that, right? Let's say they're moving, colliding, and things like that. All I have to do is just add all of their momentums before collision, all of the momentum after the collision. The sum before and after will be the same. So this is what we call a conservation law. It's a conservation of linear momentum. So the sum of the momentum before and after the collision are equal. Okay. And in a way, like let's say you have this equation. That means this M1 V1 initial plus M2 V2 initial equals to this one, M1 V1 final plus M2 V2 final. That means I can come back and I say, since the momentum of the system before and after equals, then I can have this equation, M1 V1 initial plus M2 V2 initial, which is the momentum of the system before collision, then equals to M1 V2, V1 final plus M2 V2 final. That means that's the momentum of the system after collision, and the sum before and after equal to one another. All right. So those are the things that we're going to be now looking at. That means when we talk about collision, momentum of the system, during this collision, right, before and after, is exactly the same if the forces are only internal. There's no friction, no external forces, and things like that. So, for example, here, a train car moves to the right with an initial speed of v initial. It collides with a stationary train car of equal mass. After the collision, the two cars are stuck together. What is the train car's final velocity? Well, here's then what we can do. I can assume that when they collide, during that collision, you basically have nothing but internal forces, because there are on the rails, right, which are more or less almost frictionless. We can assume they're frictionless. So then we can say that momentum before and after are the same. So I have two objects, right? I have M1 and M2 before the collision. So I can write as M1 V1 initial. Well, I actually have that here. So I can write as M1 V1 initial plus M2 V2 initial, then equals to M1 V1 final plus M2 V2 final X. You can put, as I said, right, X as a subscript as well. Okay. That means you start with this, which is the general conservation of momentum equation for those two objects. But then you can see, right, object 2 was at rest to start with. So in a way, you can come back and say this is 0. Okay. And object 1 then basically coupled with object 2 after the collision. So then they basically stuck together and move as one with the combined mass of 2m, m1 plus m2. That means we have, m1 final plus m2 final. Well, they are stuck together with the total mass of 2m, moving with some same final velocity, and this is equals to the momentum before, which is just m times v initial, since object 2 was at rest. Okay, so we can see, right, and then I can just say that I can even cancel the mass because they're the same, and I can say v initial, or we can say, like, let's say v initial equals to 2 times v final, or v final equals half of v initial. And if I was given v initial, I can just find v final to be exactly half of that. Right? That means it's very easy for us to find, final velocity of the system, or, object and things like that after the collision, whenever, you're using this concept of conservation of momentum. Because during the collisions, those are the things that happen. All right, so let's again look at this closely. So if you have a system that is isolated from, let's say, environment, right? So with n number of particles inside. And in this case, for example, n is equals to 3 because you have 3 particles. So the system has a total momentum. Well, what is a total momentum? Well, is adding all the momentum of all of them together. So P1 plus P2 plus P3. And if you have n numbers, or plus Pn. Okay. So this is the momentum of the system. And what we learned, according to the Newton's second law, right, that to change the momentum, you need to apply force. Okay, but there are kind of two types of forces: internal and external. Internal and external. And what happens here is this: for all the internal forces, because they're all action-reaction forces, so those two cancel each other, those two cancel each other, those two cancel each other. So the sum of the internal forces always equals to 0. That means if I come back here, this is equals to 0 always. And what we end up with is just a change in momentum of the system will be only purely, in the hands of external forces. Okay. So the rate of change of the total momentum of the system is equal to the net force applied to the system. Net external force, right? So net external force applied to the system. Okay. Now, this result justifies our particles model when we talk about just particle, right? Internal forces between atoms in an object do not affect the motion of the object as a whole. But if the system is isolated, then net external force is 0. Well, if the net external force is 0, then change in momentum is 0 for the isolated system. And this is what we have. So the law of conservation of momentum is then the total momentum P of an isolated system is constant. Interaction within the system do not change the system's total momentum. And what we do here, we just write it as P initial equals P final. All right, so final momentum equals initial momentum of the system. All right. And what we do basically is this, right? So once you understand that, you have a collision, you look at in terms of how to define a system. What object do you have in your system, if there's an external force or not. And again, generally when we consider collisions like that, we assume that there's a conservation of momentum. Okay. So, and we can look at, is it one-dimensional or is it two-dimensional? Because you can have a one-dimensional conservation of momentum or two-dimensional conservation of momentum. So we'll see in examples of each one. And then we can write it, let's say, if it's two-dimensional, then there will be one equation for X direction, one equation for Y direction. And then we can look at in terms of, generally looking for the final speed of the object before, after collision or before collision, depending on what it's asking. So let's look at several examples like that. All right, so we have a 10,000 kilogram railroad car, A, right? So let's say the car A, traveling at the speed of 24 meters per second, strikes an identical car B at rest. If the cars lock together as a result of the collision, what is their common speed immediately after the collision? Which is basically exactly same, similar example as you know, as we just did, right, a little bit earlier. But in a way, what we can do here is we can look at in terms of uh, now there are numbers, right? But still, we assume that they're identical. So I can write as M1 V1 initial plus M2 V2 initial equals, this is before collision. Then this is equals to, since I know they're coupled together, I can just write this as M1 plus M2 times V final. Okay. Now, because M1 equals M2 equals, I can just put some M. And because object 2 was at rest, so I can just say this is just basically M times V1 initial equals to M V final, as we learned, right? We cancel those. Then V final equals to half of V initial. And since V initial was 24, so this is then 12 meter per second. You can see how easy it is to find that information. Okay. So anything else, right? Using anything else would have been, completely waste of time and, a lot more tedious. Using the conservation of momentum, just basically a couple lines and you have the final velocity. All right. So conservation of momentum, as I said, right, depends on the choice. So let's say if you're talking about a ball, oh, sorry. If you're talking about the, a ball to be your only, a system, then the force that it has from Earth, right, and when it's being dropped, will be considered as external force, and it will change the momentum of the ball. Same way, if I take Earth as my system, the force that ball exerts on Earth technically changes its momentum as well. And momentum is not conserved for that. If the ball is my system, for example. But if I take both of them as my system, then momentum is conserved because my system has momentum of the ball plus momentum of Earth, and the forces they exert on one another are internal forces, and they cancel each other. And basically, my momentum of the system before and after remains constant. All right, so one of the things that we're going to do, we're going to define, let's say, two types of collisions. When we talk about, let's say, collisions like this, there are two types of collisions. There are inelastic collisions and elastic collisions. Okay, so inelastic and elastic. So, for example, think like this: so elastic and inelastic. Okay. All right, so we're going to talk about that. All right, so the momentum is conserved for both of them. Okay, so momentum is conserved for both of them. We're going to explore them a little bit more, later on in next few chapters when we learn about energy as well. Because one of the things we have here is, in a way, the difference is this: momentum of the system before and after is the same for both collisions. But the other thing that we will see in the next chapter is that energy, which we use E for that, before and after is also the same for elastic, but it's not true for the inelastic. So they're not same before and after. So momentum is conserved, but energy is not conserved, which we'll learn in the next chapter. So those are the main difference between elastic and inelastic. So there is a special case of inelastic collision that we're going to see, which we already seen, is when the objects stick together. So they stick and move together after the collision. This is known as, sometimes known as a perfectly inelastic or completely inelastic, right? So let's call this perfectly inelastic. Perfectly inelastic is when they stick together. Doesn't mean every inelastic collision objects stick together. No. But when they do, we can call that perfectly inelastic or completely inelastic. You can write perfectly inelastic or completely inelastic. And we know then right away that it's an inelastic collision. Okay. So examples of inelastic collisions: a piece of clay hits the floor. It sticks to the floor, right? A bullet strikes a block of wood and embeds itself in the block. Railroad cars coupling together upon impact, which you already seen. A dart hitting a dartboard. Basically, all of those are examples of, in a way, perfectly inelastic. Again, as I mentioned, Not every inelastic collisions objects stick together, all right? But when they do, we know definitely it's perfectly, it's inelastic, because in no collisions that are elastic, objects would ever stick together. All right, so let's look at then a couple of examples of, of inelastic collisions, or perfectly inelastic, let's say. A 300-gram bird flying along at 6 meters per second sees a 10-kilogram insect heading straight toward it with a speed of 30 meters per second. The bird opens its mouth wide and enjoys a nice lunch. What is the bird's speed after, immediately after the swallowing? Right, so something like that. So we have two objects, bird and the insect, right? And they're moving toward each other. And then after that, when the bird swallows the insect, now you can think of like they are stuck together and move as one, which is an example of perfectly inelastic collision, right? So then we can say that this is basically uh, M1 V1 initial plus M2 V2 initial equals then M1 plus M2 times V final. All right. So then I can write this as um, 0.3, which is the mass of the bird, right? 0.3 times 6 plus, and then 0.01 for the insect, then minus 30 for the velocity, and then it's equals to zero point 0.3 plus 0.01, then times V final in a way. Okay. And then, you can try to go ahead and, calculate that, right? So that means, V final in a way will be equals to, I should have probably done this, right? So basically it's M1 V1 initial plus M2 V2 initial over M1 plus M2, like this. And then, you can calculate, let's say, the velocity, right? Uh, After the collision. So let's see. All right, equals 4.8 meters per second. So it went down from 6 meters per second to 4.8 meters per second after the collision, you can say. All right, here's another one. So this is one that kind of now going to combine some of the things that we learned. Okay. So a 10-gram bullet is fired into a 1 kilogram wood block where it lodges. Subsequently, the block slides 4 meters across the floor, where the coefficient of kinetic friction is 0.2 for wood on wood. What was the bullet's speed? All right, so let's do a rough picture, right? So think like this. So here's a bullet, here's a block, here's a bullet, and this is in a way it has two parts. So first, this is my M1, this is my M2, and I have V1 initial, where V2 initial equals to 0. So this is before the collision. Now after the collision, since it lodges, right? So now the block and the bullet, right? So that the block and the bullet inside going to be moving with some V final. It's a perfectly inelastic collision. But because there's a friction, right? Because there's a friction, it's going to slide 4 meters, right? Going from this X initial to this X final, where this is 4 meters. Let's say this is 0. It's going to go ahead and it's going to stop. So in a way, I can say then this is, let's say this is point A, and this is point B, and let's say we can say that velocity at point B is 0 of the system. Okay, that means in a way you can say then velocity final after the collision is equal to my velocity at point A. That means this is a collision problem. This is just a dynamics problem, dynamics/kinematics problem, and we're going to be then have to do step by step in order to find all that information. Because, for example, if I look at the first part, which is just a collision, I have this, right? M1 V1 initial plus M2 V2 initial equals then M1 plus M2 times V final. Well, this is being 0, so this becomes m1 v1 initial because the black is at rest, then equals to m1 plus m2 times v final. The only problem here is, remember, my goal was to find m1 initial. So if I divide this by m1 initial, divide this by m1, I can then solve for v1 initial, because that's what I want, right? Bullet speed, initial speed. But I can't because I don't know what the final velocity after the collision is. So I have two unknowns in that one equation. That means now I have to go back and use the other things, which is, Newtonian dynamics / kinematics. And my goal will be obviously to solve for this guy, which is basically same as v at A, right? Because here's what I have. I have then the black and the bullet together, right? So let's say lodged with some velocity at A, where xa is equals to 0. They move to the point B, which is 4 meters, and they just stop. Vb equals 0. So let's say, can we find what is the velocity at A? Well, obviously we can, right? Because we learned how to do that. I can look at then in terms of what are the forces acting on the object. So there's a normal force, there's a gravitational force, and there's a friction because we're given coefficient. That means, in an x direction and a y direction, if I do my force table, I can see that there's a kinetic friction, normal force, and the gravitational force. So this is negative Fk, 0, 0 plus n, 0 minus mg. And my net force, this is 0 because only going to be sliding along the x-axis, but this one, m times a. So my equations are like this. Negative Fk equals mass times acceleration. And equation 2, then normal force equals then basically mg, right? Because n minus mg equals 0. Which means now I need to find acceleration. Remember, so in order for me, because I know final speed is 0 and I know displacement, so I can try to find initial speed or initial velocity. And I can do that if I find acceleration. And I can do that because equation 1 is negative mu k times normal force equals ma. And normal force is I just said mg, right? So negative mu k times mg equals ma. See, the mass cancels out. Then a equals negative mu k times g. That's it. And I can solve for a because it's 0.2 times 9.8. I'm going to get negative 2 meter per second square. All right. That means this is my acceleration. Now that I have acceleration, all I have to do is just use kinematics because it's a constant acceleration and I have displacements, right? Delta x equals 4 meters. I have final velocity, which is 0. Then I can use the equation 3, kinematic equation 3, remember. V final square equals V initial square plus 2 times acceleration delta x becomes 0 equals V initial square plus 2 times A delta x. And then just solve for V initial, which is negative 2A delta x and square root. So it becomes negative 2 meter per second square times 2, right? And then times the delta x, which is 4 meters. V initial, or V, this is V initial, which is basically V at point A, right? So this will be 4 meter per second. That means the collision produces black bullet velocity of 4 meter per second after the collision, right? That means my V initial, which is then my VA, which is then V final of the after the collision. Then I can come back and use this to solve, for that. So mass 1, let's say that's the bullet, right? So 0.01 plus 1 for the bullet, right? For the black, divided by 0.01, then times 4 meters per second. So if I do that calculation, I'm going to get V1 initial, which is velocity of the bullet before the collision, as 400 meters per second, which technically matches what I would expect for the bullet velocity. So generally like around anywhere between 300 to 600 meters per second. That's how fast bullets are moving. All right, so that's why you can see, right? This is an example where I combine kinematics, dynamics, and concept of momentum to solve a problem like this. All right, so we can also have what we call explosion, which is basically you have maybe like two, one object explode and becomes, let's say 2 or 3 pieces, right? Break down to 2 or 3 pieces. But still, when they break, they push each other and with the internal forces. And if the system is isolated, the total momentum of the explosion will be conserved. Okay. So for example, a rocket is a perfect example of that. Before, right, you have the rocket and the fuel, and then after that it dumps the fuel. But when it dumps the fuel, right, like let's say, don't remember the action reaction, you dump a fuel, fuel pushes you upward. But you can also say that they break, and you have then momentum of the fuel plus momentum of the rocket together combined gives you zero because initial momentum was zero. Okay, so those are the things we can say. That means because initial momentum was zero, final momentum should also be zero. That's why they have to be moving in the opposite direction for that, to happen. Right. So we have another example similar to that, which is, the let's say you have a rifle. So calculate the recoil velocity of a 5 kilogram rifle that shoots a 0.02 kilogram bullet at the speed of 620 meters per second. Remember, if you ever you shot a rifle, when you shoot, the rifle kind of recoils backwards. Why? Because of that action reaction force from the bullet, and also because of the conservation of momentum. Because right now, this is before, I can say the momentum of the system is momentum of one, let's say, or momentum of the bullet initial plus momentum of the rifle initial equals zero because they both at rest. But this is also should be equal to the final momentum, which will be momentum final of the a bullet plus momentum final of the rifle. Right? That means the zero is equals to mass of the bullet times velocity of the bullet plus mass of the rifle times velocity of the rifle. Okay, which means then if I want to find the recoil velocity, I want to find the velocity of the rifle. So then m rifle v rifle is equals to negative m bullet v bullet. That means velocity of the rifle is equals to negative velocity of the bullet over velocity of the mass of the bullet over mass of the rifle times velocity of the bullet. Then velocity of the rifle equals negative, and then 0.02 over 5, that's the mass ratio, then times 620 meters per second. Then velocity of the rifle basically will be in terms of that, right? So should be negative 2.5 meter per second. All right, so that's why it's to the left, right? That's why if you calculate this, this will be exactly the same amount as that one, but negative. That's why they add together, gives you zero because the initial momentum was zero. All right, so then in a way, what we have, the last thing is basically two-dimensional conservation of momentum. That means, for example, you have an object moving to the right, the other one moving up, and then they collide here. They can then stick together, move as one, or maybe like, let's say one is moving like this, the other one is at rest. So when they collide, it's not a head-on collision. So then after the collision, let's say this one moves like that, this one moves like this, right? And so on and so forth. So you can have different collisions where they're not one-dimensional, but two-dimensional. In that case, you get two equations. One in the x direction, conservation of momentum in the x direction, and then conservation of momentum in the y direction, right? So you have to kind of like look at it in terms of this. So I give you an example here. So let's say you have a 900 kilogram car traveling east at 15 meters per second. So let's say you draw a coordinate system and say, all right, so here's my my car like this. So this is my M1, V1, and collides with a 750 kilogram car traveling north at 20 meters per second. And here's the second one, M2. So we say that, one is going north, the other one going east. So then this is V2 initial, this is V1 initial. The cars stick together after the collision. And we can assume that they collide here, the origin, and they stick together. Assume that any other unbalanced forces are negligible. What is the speed of the wreckage just after the collision? And in what direction does the wreckage move just after the collision? Because we know that, if they're moving like that, after they collide, they're probably going to move with some final velocity like that and with some angle theta. And that's what we want to find. That means our goal would be to get that. All right, so you can see, right, if I'm looking at this, the final velocity can be broken down into v final x and v final y, right? And then when I'm doing my equations, right, so when I'm doing my equations, I can say, all right, so I have two equations in x direction, m1 v1 initial x plus m2 v2 initial x equals then m1 plus m2 v final x. Basically, I can put it like that. Then, for the second one, I have then m1 v1 initial y plus m2 v2 initial y, and this is equals to m1 plus m2 then v final y. All right. So now there are a number of ways we can solve this problem, right? Number of ways we can solve this problem. So I have a solution that I have on the slide, and I'm going to give you a little bit different one this time for the video. Think like this. So you can simplify a little bit right now because see, object 2 has no horizontal initial velocity and object 1 has no vertical initial velocity. Okay. So then what I can do is this. So I have basically kind of simplified my equations, right? Kind of simplified my equation. So it's basically m1 v1 initial x equals to then m1 plus m2. Then what I have is this. So v final x. What is v final x? Well, using this, I can see that this is just v final cosine of theta. All right, then second equation becomes m1 v2 initial y, right? So equals then m1 plus m2 times v final y. What is v final y? Well, let me actually do it like this. I'm going to write the second one on top. m1 v1 m2 v2 initial y, right? Because since this one is a surviving, and this is equals to then m1 plus m2 then v final sine of theta. So this is in the x direction, this is in the y direction, whatever survives. Then I'm gonna do the same thing as we've done before, divide them. Well, if I do that, here's what I get. M1 plus M2, M1 plus M2, V final cancels out. Once I get that, then what I have is this. The right side, just sine theta over cosine theta, becomes tangent of theta. The left side is m2 v2 initial y over m1 v1 initial x. All right, so that means I can say that tangent of theta is equals to m2 v2 initial y over m1 v1 initial x. And I can use this to solve for theta. Right? Because what is m2? Well, I'm given that, right? m2 is 750 kilograms, and its velocity here is 20 meters per second. Divided by then this is 900 times 15 meters per second. And I can put that and find the theta. And this will be 48 degrees. 48 north of east. Okay. Well, once I get that, then I can go back to any of this equation. So let's say modified equation. So for example, modified equation for the x, which is m1 v1 initial x equals then m1 plus m2 times v final cosine of theta. You can see, right, now that I have theta, I can say then v final is equals to m1 v1 initial divided by m1 plus m2 times cosine of theta. And I have everything. I have m1, I have m2, I have cosine of theta, and I can directly solve for v final, and this will give me 12.23 meters per second. And that's going to be my final answer. You can see, right? You can also do it like this. I have a different version, different way of solving on the slides. So you can look at that, every problem, there are a number of ways you can solve. All right, guys. So then this concludes chapter 9.